Thank you, thank you. Also, thank you for the Italian correct pronunciation. Yeah, it's Cagliari. It's hard to say. Okay, so hello everyone. It's good to be here. Today we are talking about machine learning security, and it's been my research topic for a few years now. My talk will cover mostly what we do to evaluate machine learning models for security purposes in general. And there are some misconceptions that are usually related to assumptions we make on the machine learning model or our evaluation that we will break down today. And we will see what we did wrong in the past, what we can improve. If you are familiar with the field, if you're not, no, don't worry, I have a few slides to cover. But if you're familiar with the field, you might have seen this matrix here with this table, where machine learning attacks are mapped together with cybersecurity concepts. And basically, we have integrity, availability, and privacy issues, like any other cybersecurity system. In fact, we can think of machine learning as software in the end. This is a spoiler for what I will say after, but it's my view, my personal view of machine learning. When we are deciding whether to use machine learning or not, in general, we have to think of it as additional software that we can use or not use, and it has its own risk if we adopt it. And today we cover mostly this top left corner that is the evasion attacks. So they are attacks on the integrity of machine learning models. So it means that the model will not behave as we expect. And it covers mostly when the machine learning model is already trained. Then if you are curious about all the other types of attacks, there is a lot of literature about it, and you can find it in the reference that I have here. Okay, so I mentioned evasion attacks. Let's see how they are done. What is the goal of an attacker here? Imagine, let's start from a normal machine learning pipeline where we have some inputs on the left. Then there is a machine learning model. And on the right side, we have the output for the machine learning model. In this example, there are images. But imagine anything you can put as input here that can be handled by a machine learning model. And this, whatever I say today covers anything, any domain, and so on. So don't restrict your mind to images in this case. What happens here is that first we have an input, then the input is mapped into features or deep features that the machine learning model can process. And then we have our output. The way we train this model is with a loss function, the one you see in the bottom right. This loss function, our goal with this loss function is to tell apart these different classes, samples from different classes. So for instance, we have parrot, cat, and dog. This loss function will be low if parrot is the output from the machine learning model. So it matches the true label of the sample. And this is general training. How do we minimize this loss? You see, we are finding this W that are the parameters of the machine learning model by changing the machine learning model itself. So we change the center part so that we can reduce the value of the loss. And that's all right, that's normal training. When we attack the model, our goal is different. We want the output to be wrong because this is the integrity attack, the integrity problem that I was talking about. Especially, we want a specific misclassification. So for instance, I can decide instead of parrot, the model has to output dog, or I can just want a misclassification. For instance, instead of parrot, any other label is fine. The way we do it, well, basically with the same thing we use for training, we use a loss function. Again, the loss function tells apart the samples, so we can also use it to make them closer together. Or we can also use it to minimize this loss function with respect to a wrong label. But here, notice that we are minimizing over a different thing. Before, we were changing the model. Now we are changing, actually, this pattern that we had added to the input. So what we change here is the input. The model is fixed. Remember, this is a model. It can be deployed somewhere in the web. For instance, it can be a Google prediction API, and we don't have access to the model, but we can modify the inputs we pass. Again, think of this as any data that we use for machine learning models, not only images. And once we found that these attacks exist, oh, and by the way, I forgot to mention, the problem here is that the perturbation can be very small. So the image will still look like a parrot, or if we have any other input, will still look like an input of the original class that is supposed to be classified, but for the machine learning model, it's unrecognizable. In fact, here we have some examples of this where we would expect the machine learning model to output something specific. For instance, in the first case, there is this guy with the colorful eyeglasses on a face recognition system, and well, he puts these eyeglasses on, and the machine learning model, even though the perturbation is small, so we have only eyeglasses, the machine learning model understands that this picture is Mila Jovovich. So it's, of course, wrong. And again, this problem is that these are small perturbations that can change completely the output of the model. If the person depicted would have looked similar to Mila Jovovich, we could have understood this. But in this case, it's a small perturbation that changes completely the integrity of the model. Then we have these other examples, for instance, the traffic signs, where we use this example mostly to show the impact of these attacks. So imagine that you are in a self-driving car and it's recognizing the traffic signs. And because of these stickers that are carefully crafted and placed specifically in some points of the image, the car doesn't see a stop sign, but sees a speed limit. And so it will crash in a car accident. Of course, this is assuming that we only have computer vision. Don't be scared. Self-driving cars are safe. Actually, they have a lot of redundancy systems, more on top of the computer vision. But, you know, it's just something that sticks in the mind of people when we show it. More interesting, to my point of view, are other attacks that are also in other domains. So, for instance, we have these adversarial audio waveforms where the original waveform is changed, again, with specific perturbation, very small. For us, we still hear the same sentence, but the model understands something different. And imagine now with all these AI assistants that hear our voice and take decisions for us, like, for instance, buying something on Amazon, if you have these kind of perturbations that can steer the decision of the model without supervision, because then the model proceeds. And finally, also very interesting is the case of machine learning model used for malware detection, where you take an executable file, in this case it's Windows executables, and with machine learning you are able to analyze it and to predict whether it's a malware or a goodware. But then there are these people who are able to hide some specific things that don't break the virus, so the malware still works, but it's not detected anymore by the machine learning model. And again, this is using very small perturbations that don't change the fact that this is a malware. Okay, so we have these all these algorithms, but let's see better how do we find this perturbation, because I said, okay, this magic perturbation can be found, but it's not random noise, definitely. In fact, I get this question often. What is the difference with random noise? So random noise is not dependent on the model. In this case, we are looking for a perturbation that is the worst case for the model. So it will be targeted to the weaknesses of the model, to the sensitivity of the model. So it will change specific parts. Okay, and we formulate this problem of finding this perturbation with two components. There is an optimization problem that we define, and I will break it down. There is a lot of math here, but I promise I will explain it. And then a solving algorithm. Solving algorithm means in often cases gradient descent, as we do for model training. So it's nothing that we haven't seen if we are not familiar with machine learning. Let's see the optimization problem first. The optimization problem defines these three components, or can be also other components, but usually we define this in a mathematical way. We have, first of all, the background of this picture here on the right. It is colorful. The color meaning is that this is the loss function. It's what I said before. We use it to tell apart the samples of the two classes or more classes. So in this case, we have the parrots, the samples of parrots in one side and the samples of dogs in the other side. And there is this line that separates them. This is where the model changes the decision. It will say parrot from one side, dog from the other side. And the color shade is how much the model is certain, let's say, of how much the sample is related to parrots or to dogs. In simple words, it's a little bit more complicated than that, but for what we need today, it's enough. So we have one point here. This point is the original sample that we want to change. It's a parrot, as the example from before. Our goal as attackers is to change the decision. So we have to bring this sample to the other side of this line. All right, we have also mentioned that there is this background color that is the loss function. If you think about it, the loss function tells me in which direction to go to change the decision, which means I can use something from this loss function to know how much and where to change my sample. Okay, then we have other things here in the problem. One is a norm constraint, a perturbation size constraint. This is here for two reasons. The first one is that we want the perturbation to be small. Otherwise, as I said, there's no point in considering it as a security issue. If I have my image that is slightly changed and the model says it's a dog, it's a security issue. If I have my image that is completely changed so that every pixel becomes the pixels of an image of a dog, it's not a security issue. We expect the model to behave in that way. Okay, so we have this norm constraint for this reason, that we wanted the perturbation to be small. And then the second reason is actually when we compare models, we want to fix something. So in this case, we fix the budget of the attacker, the perturbation size, and we check how much the attacks are successful on multiple points. So I run the attack with this perturbation budget. I find that 30% of samples evade, and this is one model. Then I change the model, I run the attack with the same conditions, so the same perturbation budget, and I find that 50% of points evade. So what I notice here is that more points evade in the second case. So the second case would be more affected by adversarial examples. Okay, then we have another constraint here. This third constraint is very important, is to make sure, in this case, it's one for the images, but usually we have constraints that make sure that after the perturbation, the sample is still a valid sample. What do I mean by that? Let's take the case of the images. The images have a representation in the digital domain. It's an unsigned integer of 8 bits. It means that every pixel will be represented with a value from 0 to 255. Integer. Okay. When we attack, if we use whatever algorithm we are using, without this constraint, we might have pixels that go, first of all, they might be floating points, and that's okay, we can round them. But we can also have pixels that go in the negative values. So we have a pixel of -3 or whatever, or we have a pixel of 500. These are problems because it doesn't respect the rules of the real world. If I try to save that image, it will not be saved. Matplotlib will give me an error, or when I open it with an image browser, it will not open. So in this case, we have these additional constraints that make sure that the sample is still valid, because this is the real threat. Otherwise, we are talking about virtual stuff. This constraint, for instance, in the case of malware, is slightly different. And the constraint is, well, if I take a malware and I modify it so that it bypasses the machine learning system, my goal will still be that if I send it to someone and they open it, it has to be runnable. If the malware doesn't work, there's no point in bypassing the machine learning system. I'm not infecting anyone with that. Okay, so we have all these things here. We put them together. The only error left is that. And now, well, we can either look for it in a stupid way, that is, I try with brute force all the possible input values. Be aware that this is a two-dimensional space, and it would be already complicated in two-dimensional space. But if I have many dimensions and I have no directions whatsoever to go, this will be very complicated. So we are smarter than that, and we use solving algorithms. I told you already that we are using gradient descent, basically. That is what we use for training. We can do the same here, because if you think about it, we have a loss function, and we have the gradient of the loss function. Well, when we train, we use the gradient of the loss function with respect to the model's weights. So we change the model weights so that the loss is minimized. We have here the same tools, we just have to minimize over the values of the perturbation that we add. Okay, so this is the optimization problem. Just again, to mention that when we want to compare models, then we fix all these constraints, we keep them constant, and we run the algorithms. If the algorithms find more points for a model than for the other, then we can compare the models and tell if they are robust. This is called, this is a metric that is usually in state of the art called robust accuracy. And usually the higher, the better. Okay, this is one way of solving that problem. The other way around is to swap the optimization. So the minimization of the perturbation will be our objective. And we put as constraint the one here that is the point has to be misclassified. So instead of minimizing the loss with a fixed perturbation budget, here we find the smallest perturbation budget to change the decision of the model. It's very cool. I mean, we like it more for a reason. In the first case, if I fix the perturbation size, I find how many samples evade. But if I change it, I have to run completely again the algorithm, because the conditions changed. In the second case, because we find directly the boundary, we can just measure how many samples flip for every distance. So we run it once, and we have a full picture of the robustness. We directly find where the decision changes. So the first case, it's faster. It's definitely easier to optimize because we have very efficient algorithms for this. In the second case, we don't have very efficient algorithms, or at least we're trying to improve it, of course. The optimization is tricky, but it's what we desired for evaluating robustness of a model. So here is a list, non-comprehensive. There are even more algorithms of the algorithms that were published for solving these two problems, these two problems or variations of them. I have my own contribution here. It's a 2021 paper where we have developed an algorithm to find the second case that I told you about. So smaller perturbations so that they evade. And the strategy was to take all that we know about existing attacks, remove the downsides, and add and take all the good things they do. So usually the limitations of these attacks are these three. First of all, some of them have long runtime. What does it mean? It means that if I want to evaluate my model thoroughly, I have to launch an attack and wait for it to finish before I know how much my model is affected. And I have to do it multiple times because these attacks they need configuration. So If I'm lucky, I find the best configuration and I know that my model is vulnerable. If I'm not lucky, I might have to spend more time. Well, actually, I will never know if I was lucky at the first try because it's empirical. We'll come back, we'll circle back to this concept later. Second problem of existing attacks is that, as I mentioned, they have to be configured. And often this means that I have to choose a learning rate. And, like what we have for training, we have recipes for training models, but all of this is empirical. There is no theory that says you have to use this learning rate. You have to use this projection. You have to use this loss function. Even worse, there's no way of predicting it. So I have just to run it from scratch every time. On top of that, for every domain, usually these parameters are different, even for every data set, often. Okay, and then finally, limited threat models mean that I cannot really customize it to my need. Again, this has a lot to do with the type of data we are handling. If I handle images, I have different constraints than when I handle software. So all these downsides, we try to surpass them with an algorithm. I will not go through the details of the lines of this, but I have a picture to show it. Here is similar plot from before. So we have a decision boundary. It's actually very white in this slide, but imagine there is a decision boundary and you have a point. Again, the goal is to bring it to the other side, but this time, not to find any point that is in the other side and within the constraint, but to find the smallest perturbation, so the closest point to this one that will be misclassified. The way we do it, well, let's go to iteration K, because the first iterations is just exploration of the space to find a direction at the beginning. At iteration K, so after we do a little bit of exploration, we try to understand if the exploration we did is enough. We do it with that decision-based rule. So in this case, I have this perturbed point at iteration K. What I do is ask the model, is this misclassified? If the model says, no, it's not misclassified, I will enlarge the region. So I will try to find an adversarial example in a smaller region. If the model says, yes, it's already misclassified, then we try to reduce it and to find an adversarial example with a smaller region. In this case, it's not misclassified yet, so we enlarge the region. And then the second part, and this is basically the green block that I have in the left. Then the second part is just projected gradient descent. That is the algorithm that we use for minimum distance attacks. Sorry, for the other case, for the maximum loss. Okay. So we combined basically in a one single line. This is projected gradient descent, so the efficient algorithm we have for the other case of optimization, but with an adaptive constraint, so we can find the smallest perturbation here now. All right, and that was a publication from 2021. I mean, we achieved we removed the problems of the other attacks, or at least we surpassed them in the cases we tested. Then what we did after was, well, since we have this algorithm that is kind of efficient, what we can do is extrapolate whatever we use for optimization and frame it in a software framework that is very well developed for optimization. That is the PyTorch framework. So we implemented the attack by abstracting the optimizer, the loss, and the system that decides the step size, basically. That is called the scheduler. And we extracted them from the attack, and we make them configurable. You might think, oh, why did they go through this stuff? Is completely useless. Actually, no, because then once we unlock this, we can use the implementation from PyTorch, and this is one thing. Of course, it's more efficient than ours, and it will reduce the time needed for the evaluation. But most importantly, we can use something that is already designed for training. So in this case, we used hyperparameter optimization framework. So it's a framework that runs a few simulations and finds automatically the perfect hyperparameters, at least perfect, the best hyperparameters on the set that I define that give you the best results. So in this case, we are not implementing something from scratch. We are just reusing something that is well developed for training. The result, and this is a link to the next thing I will discuss. The result is, you see this plot on the right. We have two curves. This is the accuracy with increasing perturbation sizes. So the more perturbation we add, the more we expect the accuracy of the model to drop because we have more power. And we have two curves, but this is the same model. So we are not changing the model, we are changing the way we evaluate it. If I evaluate it with an attack that is suboptimal, I get the default, the red curve, which means the accuracy is not as affected as I usually actually have with the strongest attack. This is key to understand what I'm gonna say next. So if I use a weak attack, I might have a suboptimal evaluation, which if I trust and I deploy my model, can be leveraged by the attackers. So let's go first and discuss a little bit about defenses, because, okay, I said, well, this model is robust or not, but I didn't say how to achieve a robust model. Over the history of adversarial attacks, people started thinking, well, how can we make the model less sensitive to these perturbations? Well, one and the first that was presented is called adversarial training or robust training. It looks scary as an equation, but actually, if you decompose it in what we already know, it's kind of, it can become more easy to understand. First of all, we have this min and max. Let's look at the max first. This max is finding the smallest perturbation. Well, actually, it's optimizing this delta, the perturbation, to maximize the loss function of a model. Delta is here, so it's the perturbation that we add. So the inner problem is finding the worst case adversarial perturbation for the model. The outer is finding the parameters of the model. So it's finding the model that is less affected by the adversarial examples. This is the optimization problem again. The way we solve it is the most straightforward way possible. We have a few points. We train a model. Here, of course, we can understand this is not a robust model. If I find the perturbations, some samples will flip to the other side. We take these samples, we label them with a correct label. So these samples that are red and they went to the other side of the boundary, we label them as red again. And we train a model that is less sensitive to this perturbation. So we put the adversarial examples in the training loop. And this is the only one that has withstood the test of time so far. There are other strategies that can work in limited conditions, though, and I will explain later. They are usually detectors. So in the sense that I can pass my sample, before giving them to my machine learning model, I will use another model to understand if the sample is an adversarial example. I can use some filters that are handcrafted, so they have some signatures that tell you, okay, this is an adversarial example, don't classify it. Or I can use machine learning models again. Okay, two things to notice here. Well, this is, first of all, we add a reject option, so the model can decide not to decide. It means that some users will be not happy about it. So it will have, if we have false positives, some benign users will get a decision that is, oh, I don't decide. And then the other problem here that I see is okay, if it uses a machine learning model, I can also define an optimization problem that minimizes jointly my detector loss and my model loss. So I make an adversarial example that breaks both models. So I'm back at the first issue. I still have adversarial examples. The problem, the reason why people started thinking other solutions rather than adversarial training is because adversarial training is very costly. So I have to create the adversarial examples, and I mentioned already multiple times, this takes time. If I have to train and also make adversarial examples and possibly do it multiple times, this is very, very expensive. So it takes very, very long to compute, to adversarially train a model. Detectors can be bypassed. So the third category of defenses we have is what we call, unfortunately, ineffective defenses. They are defenses that try to be creative, to remove the adversarial examples, but actually they only make the attacks more difficult in the end. And there is a long history of these defenses. Actually, this is a list, again, just some samples taken from history. There are a lot more of defenses that have been published in top venues, and they have unfortunately been broken. It's even worse because they have been broken even knowing there are guidelines around that tell you how to properly evaluate defenses. And this line in my slides stops around 2020, but it goes on and on again. I'm also a reviewer for many conferences, and I'm seeing this pattern repeated over time. It's never ending. And there is a specific reason for this. The specific reason, you might have heard it already from my previous slides, is that we are trusting an evaluation that is empirical. So we have these attacks, we configure them. Let's say I import my library with all the attacks, I instantiate the attacks and run them. Then at the end, will I get log information? Will I get something that is more than just an output? No, I just get the adversarial examples returned by the algorithm, and I don't know if my optimization was conducted well or poorly. There are, I have examples of this, okay, so it will be clearer after. The problem is, if I run an empirical evaluation, I'm considering machine learning as software, so I'm doing test cases, I'm evaluating test cases on the model, but it's not exhaustive. So I don't have any guarantee that if I found nothing, the model will actually be robust. This is a key point of evaluating models, and people often forget about this. So the second problem that we have in evaluation often is that we don't consider that behind these algorithms, there's hidden an optimization process. And this optimization process is making assumption. This is a key word here. I might skip this slide, it's not important. The assumption, most important assumption we make, is that gradient descent can work. So if we use all these attacks that leverage these algorithms, these powerful gradient descent algorithms, we are assuming that the loss function looks like this. So we have a signal that we can follow to minimize it. However, there are cases in which this doesn't work. So in this case, in the first case, it was a defense leveraging distillation techniques. And the effect of these distillation techniques was actually to saturate the loss. So we have values that are very high or very low, but it's behaving like a loss function, a step function. So we don't have a clear direction on where to go to improve it. It's completely flat. However, we know it's not non-existent. So we know that there is a point in here where the loss drops. We are just unable to find it with gradient descent because the assumption doesn't hold anymore that this is easy to optimize. Okay, the second case is slightly more complicated. It was a very specific activation function that was used by the authors to cause gradient descent to fail. But of course, again, here, if you compute the gradient, you can take a step in the direction of the gradient. You will have a small minimization, but then you end up in a minimum and you are not able to jump out of it. The problem is, again, that there is a direction for which this is reduced. So we are not removing the adversarial examples. And in my opinion, the only way to improve the robustness of a model is to change the boundary, not change the loss function that we use for training or for computing the attacks. So it means that these people, well, of course, they didn't know about it before, but they were making the adversarial examples just hard to find, but they were not removing them. Again, empirical testing did not reveal this. So what we did was reveal them in a systematic way. So develop some indicators, some sort of debugging tools for the evaluations, so that if I know this problem is happening, I have a direct fix to apply so that I can patch my evaluation and improve it. And then we map them to the solutions, because if you know that there is a problem, you also have to give a way to improve it. In these cases, well, in the first case, the saturation was due to a softmax function that, if you know how the softmax looks like, it's very easy to saturate to 0 and 1. If you remove it, you have a more well-behaved curve, and so you can optimize. So it's just changing the loss that we are optimizing in the end. You can use a different loss that is not saturating. In the second case, it's slightly more complicated, as I said, because instead of leveraging the gradient only at the point where we are computing the gradient, we average the gradient in an area. So we take a few samples around and we average. In this case, you see that if you take the gradient in many points here, there is a direction for which the gradient is consistently decreasing. And if you take the average, it's likely that you will get that direction. The more points you use to smoothen this function, the better, of course. But it takes more time. Okay, these were only two of the failures we found in the evaluations, but we have an entire framework now where we identified what can go wrong in the evaluations. Again, test cases. Here, you can also run the evaluation. None of this is flagged, but still you have a suboptimal evaluation. However, at least you know you're not making the mistakes of the past, like software debuggers do in the end. Okay, and then we map these indicators to the solutions that we know. And then we were able to improve the evaluation of models in a semi-automatic way, in the sense that I run an evaluation, I find the issue, I fix it, and I find a robust accuracy that is closer to the real one, which is lower than the one I had before fixing the evaluation, of course. Interestingly, we also found many bugs in the implementation of the most used attacks in these libraries. And you can imagine the cascading effect this has if you think about how many papers were published by using these libraries. So it's a very relevant and impactful contribution to investigate over the implementations as well. Finally, and this is the third point that I want to stress about real-world evaluation and what can go wrong when I want to evaluate a model from scratch. I will talk about what we can do after we run our evaluation with gradient descent. Gradient descent, by the way, is just a tool. We have better algorithms, definitely, they are just most costly. So the first step is, of course, use the easiest way to find adversarial examples, gradient descent. If I don't find them, usually we have other options. One option is I can use another model, we call it surrogate model, create the attacks with this model. So let's go back to the images. If I create an adversarial example with images, it's still an image, right? So I can feed it to another model. That is my target. So I will use a surrogate model to create this with the gradients of the surrogate, and then transfer. So just take the images crafted with my surrogate and launch them on the target model. And for some reasons, this sometimes is effective. It's mostly because models tend to learn similar things, similar representations of the data. So it might happen that you actually have what is called the transferability between models. In the second part, instead, you can also optimize without the gradients. So you take the model and you inspect couples of input and output, and find a direction for which you can change the outputs correctly. This is more costly than using gradient descent, but sometimes when you evaluate models for which you don't have a gradient, this is the only option. So there are cases in which this is actually the only strategy possible. And there is a problem, another problem related with real-world data that often people forget. When we evaluate a model, we assume, again, this keyword, assumption, we assume that the data are static, that we train our model, we deploy it in the wild, and then it will act in a predicted way. Let's say we achieve robustness. We have a model that promises to be robust, but in this case, for instance, this example is given with Android malware analysis. In this case, we have that over time, the model is behaving worse. So it's just adding more misclassifications. And it's not because there are attackers. Well, actually, yes, might be also because there are attackers. But the real reasons might also be that the data, the underlying distribution is changing over time. So this is an hypothesis that is often forgotten when we evaluate models, especially in cases that are not images. The image is not likely to change over time unless there are camera resolutions, etc., taken into account. But with malware and cybersecurity data, this is a key point to stress. Just an insight on what's happening here. So this is an example in which we are using specific API calls to tell malware from goodware. In this case, we have this common API and this evil API. It's what is, for instance, activating the camera in our phone. Okay, and we know that if we have the only the common API, our data is safe, our Android application is safe. But if we have the combination of this common API and the evil API, we have malware. With Android data, if you ever tried to develop Android software, you know that APIs get deprecated. So let's say that the attacker doesn't have anymore that API to use. What happens is that that API, that feature will disappear from our data. So in the next prediction that I will not have a way to tell apart this malware from the goodware. So the malware will go in the other side, hence the drop in the accuracy. The other case might be the opposite. So if the attacker understands that the combination of two features is used to distinguish between his malware or her malware and the benign data, then they can start injecting APIs so that the malware goes in the other side. And again, we have a drop in accuracy, a drop here actually in the detection rate directly. And the open problem that we have is, well, are these two things the same thing? If I make a model robust to adversarial perturbations, that is the second case, will it be robust to natural changes in the data? This is still an open problem and for which we have a benchmark. So we are also trying to move towards different applications than images and investigating industry relevant scenarios. In this case, benchmarking robustness for Android malware is a significant area where still we have lots of open problems. If you feel like you might want to give it a try, you can find all the tutorials in the challenge. Let me wrap up so we can conclude here. I presented basically 3 problems that we have and we are trying to fix in machine learning security. The first one is that we have a lot of tools, but we are just using them blindly. So it doesn't matter if I have many, I might have just a few of them that are working. It's just a matter of how to use them correctly. The second problem that we have is that if we use them blindly, even if we have the best tools, they can be still flawed. They can be the wrong tool for this specific model that I'm evaluating. So this is actually what we have to consider. And we have to find, for every model that we want to test, the strongest attacks. Otherwise, what I'm doing is nothing. I'm not testing the model. I'm just testing the use cases that are the most stupid ones. But attackers are not stupid usually. Okay, and the third problem is that we have to think about the real world. And I have one final slide about this. I just want to give you a little hint on tools that you can use, and then I will come back to this problem here. Because, okay, I mentioned all these things. We're trying to incorporate them in a library that will include, again, as I said, multiple tools, even importing them from existing libraries, but also incorporating them with debugging tools. So you will have a loss function that you can inspect. You will have, actually, I have a video about this. Hopefully it will be played correctly. Yes. So in this case, it's again images, but you can think of any data. But you see, you can inspect, for instance, the norm of the gradient to check if it's flat, the loss to ensure that it's improving over the optimization, and other important aspects. And this is using TensorBoard. It's a tool that we use for deep learning, so it's nothing that we've developed from scratch. It's just putting things together to make them usable by the general public, or by, I mean, at least machine learning engineers and cybersecurity engineers can understand this kind of things. Okay, coming back to the real world, I have this example of a machine learning model that was tested probably even against adversarial perturbations, and very well. It's the taxis, the autonomous taxis from San Francisco. But what people forgot was to put it in the real world, so to test it in vivo with, you know, the entire environment that it can be surrounded with. And they forgot that, well, the people that don't want this system to work, they are not concerned about having small perturbations. They're not concerned about being imperceptible. Here, they want just to stop these taxis. So they put a traffic cone that is clearly visible on top of these self-driving taxis, and they stopped the entire thing. So the company that was providing the taxi, well, they removed the drivers from the taxi, so they were paying fewer salaries probably. However, they had to pay people. They had to put people back to remove the cones physically from the car. So this is an example of what you don't have to forget, that you have to consider the entire system, not only the machine learning model in isolation. All right, and that was my last slide. Here are a few links. There is a related seminar if you're interested about machine learning security. So if you want to click on a link here, that's probably where you're going. And for the rest, I'm open for questions.